and it's really nice to be here. This is joint work we did with Agustín Borgna, so he can stop me and if I mess up. The aim of this work is to take quantum program into a low-level intermediate representation. So first of all, we want to take a quantum program. We need a quantum programming language. So to start off, we begin from Proto-Quipper-D, which is an extension of Proto-Quipper, which itself is a formalization of the Quipper programming language embedded in Haskell. So here we have a small example program which takes no input and returns the 0, 0 bell state. And here we have the compilation into a simple circuit. The main reason we chose Proto-Quipper-D as a starting point is the D, which stands for dependent type. So here we have a program which takes a list of size n, and it takes those control qubits and it applies a C0 against a single state. Now, in order to compile this into a circuit, we need to instantiate this n, the length of the list. So if we, for example, choose n equals 3, we would get this diagram. Well, this is our starting point. Now, we would like an intermediate representation from here to here. A good candidate is the SZX-calculus. So show of hands, how many know? I saw a few posters. Yeah, fair bit. So I don't need to really get into detail like what's the why why this is a useful resource, but just for those of you who don't know, SZX is a graphical language designed to reason about unitary maps between qubits. It's useful for optimization, program verification, and so on. So we have our program. The thing is, wires in SZX carry 1 qubit of information. So in order to represent the diagram, in order to represent, for example, the program from the previous slide, we would need to, again, instantiate how many qubits we are working with. So enter SZX, Scalable ZX, which is an extension of the ZX-calculus, where where they introduced this splitter and gatherer nodes in order to send more than 1 qubit of information through this bold wire, which is tagged with the arity, with how many qubits are going through it. So now we can, for example, take the little C0 program and represent it like this. Now, this is it depends on the n, on the length of the vector, but it does a C0 where the state comes from here, it gets looped around and applied the n times and goes out in the last cable. Now, This may seem like some new expressivity, some new something like it cannot be done in SZX, but it is not. Since we are defining the length of the cable, well, just we can unroll our loops and we get a valid SZX diagram. It's another way to interpret the information, and the advantage is that we're only using this constant amount of nodes. So we have our starting point, Proto-Quipper-D. We have where we want to get to, which is these scalable ZX diagrams. So let's talk about the translation. So we the domain of our translation is a reduced calculus. We call it lambda sub d, which takes parts of the original Proto-Quipper-D specification and well, cuts a lot of the rest. For example, we cannot encode non-terminating programs in a SZX diagram because we don't have infinite loops. So in order to do that, we took away the explicit recursion, but we defined a small set of primitives to work with vectors. The advantage of this is that they are bounded and the programs should be terminated. Then we define our type system like this, where we split our types into states and parameters. Morally, which this is splitting between classical and quantum data. The parameters will be the information that we can copy and reason classically about, and the states are qubits. In this case, our parameters are just natural numbers and vectors of these numbers, but it can be extended. So how do we define the translation? The translation is defined over type judgments. So if we have a type judgment of this shape, it means that this phi, our parameters, our parameter context, will give us a family of SZX diagrams which go from the interpretation of the state context into the interpretation of the type. Which, well, you may ask, what is the interpretation of these types? And it's fairly simple. It's the arity of the cables. So if I have a qubit, well, in that case, it's one. Just one piece of information will go through the cable. If I have vector, it will be the interpretation of the type times n, and the interpretation of the map, it's, since we're working with SZX and closed compact monoidal category and all that nice stuff, we can say that it's the same as the interpretation of the tensor, which is putting the cables on top of one another. It's just a sum. So the parameters will tell us about the, oh, it's dying. Oh, that will tell us about the index of the family of diagrams, but do not affect the shape. the states, for example, when we're working these kind of judgments, for example, the lambda abstraction will give me this shape of diagram. The application will give me this shape of diagrams. And what happens when we have a type judgment that works with both parameters and states variables? Well, in that case, we get something like this. Here we have a primitive of the language, the for, which basically iterates over a vector, b, and performs program m. Now, here we define a list instantiation operation, which basically copies the length of this list diagram, and for each copy, it passes the element of the vector as an argument. The other cool thing about this is that we can encode branching. We can encode conditionals. In the if 0, which checks if this natural number is 0 or not, well, in that case, we can split into two diagrams, which if this L is 0, well, it will take all the arity of the wires down here to 0, which can be proven to be the same as the empty diagram. So we're left just with the top part, and the other way around if it's not 0. So with this, this is just the example. We define the translation over all the type judgments, but time forbids to go over them all. But with this translation, well, QFT, the star algorithm for this kind of for these kinds of presentation, do not mind the lambda term. It's never easy. It's never nice to write lambda terms for algorithm. Just concentrate on these parts. We define the algorithm in 3 parts. If we were to compile this into a circuit, it would take an order of n squared n to the power 2 gates. Now, with our translation, we achieve this. We have a control rotation. Now, check that even though we are using SZX, the indexes are the family of diagrams, do not operate only on the wires. Here they are constant too, but also on the spiders. We can apply this control rotation many times. This is using the list instantiation. So we're saying we'll be applying it to every qubit sans 1, sans 2, sans 3. And the QFT algorithm per se, it's just like the CNOT example. It's just this diagram we defined. Well, apply it 9 times, loop it around, and out comes the result. So one thing to note about this operation is that it may linearly grow on the size of the nodes we're using, but it always keeps the shape. It always keeps the structure of the diagram. So we had the diagram compilation. Usually, these quantum circuits would take n square gates. Well, here it at most grows linearly. And I really like this. This representation is kind of basic. But in summary, we started from formalized high-level quantum language. We took a fragment of the language, defined a translation for it, and output our concrete family of diagrams into SZX, which itself, when passed an argument, can be transformed into a ZX diagram. After this, we have a few lines of work remaining, mainly proving soundness, giving a categorical semantic to our fragment, proving soundness, which is why I'm here. It's in a short term, encoding different algorithms, but that might be for another talk. So thank you very much.
Thank you.